because this is the most fun you can have saying a word in chemistry. Stoichiometry. Go ahead. You can do it. Don't be shy. Stoichiometry. 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 Isn't it fun? You'll feel better if you say it, I promise. Go ahead. I won't record. I'll pause. Fine. Fuddy-duddies, sticks in the mud, whatever. So we're going to spend the next probably couple weeks talking about stoichiometry. And you have actually, you might be shocked to discover, you've already done stoichiometry. You've already done some stoichiometry. In Chapter 3 and in Chapter 7, you've done bits of stoichiometry. Because there are two kinds of stoichiometry. And the first kind of stoichiometry is composition stoichiometry. So stoichiometry is all about mass relationships in chemistry. And the composition stoichiometry is just how many moles of copper are in 500 grams of copper. What is the mass of 2 moles of aluminum? That kind of thing. And then in Chapter 7, because you started talking about compounds, you started doing composition stoichiometry with compounds. So how many moles of carbon dioxide are represented in 150 grams of carbon dioxide? What is the mass in grams of 11.2 moles of sodium chloride? So you've done composition stoichiometry. And you know that stoichiometry always starts off with a what? Factor label, with a given in the first box. And we're just going to do factor label after factor label after factor label. But now what we're going to do, because now you know how to write chemical reactions, now we're going to start doing reaction stoichiometry. And this is where we look at the relationship between a reactant and a product in chemical reactions. This is always where it feels to me like it really gets real. Because if you want to manufacture something through a chemical process, you need to know how much stuff you put in to get out your desired result. And, you know, if I want to make 500 grams of iron oxide, or of pure iron out of iron oxide and aluminum, how many grams of aluminum do I need? So this is very, very real, suddenly. When we start doing reaction stoichiometry problems, and we'll be doing these on Monday, basically, there are 4 types of reaction stoichiometry problems. You can have a given and an unknown in moles. I want to make 2 moles of aluminum from this reaction. How many moles of iron oxide do I need? Those aren't real common. You can do, so, you know, less common but present. You can have a given in moles and be asking for the mass that's required or the mass that will be manufactured. You can have a given in mass and be asked to go to moles. But by far, so these are all, you know, short steps. Actually, this is a 1-step kind of problem. These are each sort of 2 steps. This is really the mother of them all. That's the one that's most useful and most real. Because your balance gives you a mass in grams. So you're always going to have to input a mass of something, and you want to know the mass of something you're going to get out. So this is sort of the holy grail, and this is what we'll spend most of our time doing. We'll do a few of the other kinds, but we're mostly going to go mass to mass. How many grams of X do I need to make 150 grams of Y? Why? Because we can. Ha! Okay. Before you can do any reaction stoichiometry problem, you have to find the mole ratio between the components of the reaction. And it's just a conversion factor. You've used conversion factors before doing metric conversions, doing composition stoichiometry conversions. But what this conversion factor relates is the number of moles of A to the number of moles of B. Has anybody here ever made salt dough? Salt dough ornaments? You mix like flour and oil and water and salt, and you put, you know, cute little baby handprints in them that you then bake and your parents will hang on the wall lovingly. Yeah. So the general salt dough recipe, let's see if I can remember this off the top of my head. I think it's 4 parts flour to 1 part salt to 4 parts or 2 parts water, something like that. I don't know exactly. What measurements do we use? Cups, tablespoons, pounds? Does it matter? No, it doesn't. It's just parts. So that could be 4 cups of flour to 1 cup of salt. It could be 4 half cups of flour to 1 cup of salt. As long as the measurements are all volume measurements, yeah, it doesn't matter. It's just a ratio of how many parts of this we have for how many parts of that. And that's very much what the mole ratio is like. So I'm going to we're going to not use the next slide because I think we can do a better job just on our own. Let's talk about one of my favorite reactions. I love this one. FeO plus Al yields Al2O3 plus Fe. What kind of reaction is this? Single replacement. And this is, and I'm going to balance real quick, 3 there, 3 there, 2 there, and I think we're good, right? Okay. This is actually thermite. So, who took AP US History? Good. What year did the Golden Spike get driven? Transcontinental Railroad. Give me a decade. Give me a half century. Yeah, I think it's like 1847, 1850 something. It's, yeah, 1850s. I'll take it. We're not doing history. But historically, so you've got people building this great steel rail across this continent. You know what the hardest part of welding rails out in the middle of the prairies and the plains of North Dakota in 1850 is? Finding a place to plug in your arc welder. Nobody's going to challenge that one. There are no plugs in 1850. You're not using a big Lincoln arc welder. You're not driving it out there on your pickup truck. So how do you join sections of steel rail in 1850 in the middle of nowhere? Chemistry! That's how. So this is called a thermite reaction, and this is actually how it's done. What is iron oxide exactly? You've all seen it. You've probably all picked at it. Rust. Yeah, it's rust. Iron oxide is rust. It's iron that's oxidized. And this is just powdered aluminum, and that's fairly easy to come by. So you take these two things, they're both powdered rust, powdered aluminum, you mix them up, and then you light them on fire. Now you're not going to do this with a match. They actually use a magnesium strip typically as a fuse to light off a thermite reaction because it's one of the only things that will burn hot enough to get thermite started. I keep saying someday we're going to run a thermite reaction in here. We're going to get all this stuff. We're going to go out in the yard. We'll have to have like the fire crews on standby or something, but it'd be so much fun. So you put in these nice little powdered things and you run the reaction, and what you end up with is molten steel. Iron, actually. Pure molten iron. Well, how does that help you build the Transcontinental Railroad? Because you have two sections of rail that are sitting butt up against one another, onto which you place a hopper. And that hopper rests on top of the rails. And you put your reactants in there. You light off the thermite reaction, and what flows out the bottom and fills that space is your molten steel. And you've just welded two sections of rail together. Now, somebody I talked to recently claimed that they still do. They still use thermite to weld rail. I'm suspicious I don't think that's true, but you're welcome to investigate. I'd love to know. So anyway, thermite reaction, lots of fun, very interesting, but also relatively easy to talk about. So we've got FeO, whoops, 3 FeO, 2 aluminum, yields Al2O3 plus 3 moles of iron. Okay. Mole ratios are literally just taking the coefficients from in front of the element or the compound and making a ratio. So what we're saying here is that for every 3 moles of iron oxide you react, you're going to get 3 moles of iron out. And we got those numbers directly from the balanced chemical equation. So what do you have to do to get a mole ratio? You have to be able to write compound names. You have to be able to write a formula and balance it correctly. So chapter 7, chapter 8. Okay. What about the mole ratio of aluminum to pure iron? Well, for every 2 moles of aluminum that you put in, how many moles of pure iron will you get out? 3. Conversely, because we can run these in both directions, for every 2 moles of aluminum that you need, or for every 3 moles of iron, rather, that you need, you know that you're going to have to put in 2 moles of aluminum. How many moles? So there's the product that you want here really is the iron. This is what you're after. For every 3 moles of pure iron that you generate, how many moles of the essentially what's a waste product, the aluminum oxide, are you going to get out? 1. You're going to get 1 mole of aluminum oxide. So these are pretty easy. They're pretty intuitive. And they can go between any 2 things in the equation, and they can go in either direction. So we can also say, if we want to make sure that 3 moles of iron oxide fully react, how many moles of aluminum do we have to put in? 2. So they can go between products and products, they can go between products and reactants, they can go between reactants and reactants, reactants and products. Every single substance in that chemical equation, the chemical reaction, you can generate a mole ratio for. Questions? And this is the original slide, but I wanted to use something a little bit different. So, here you've got, tell you what, somebody read me that reaction. And the whole point here is just to look at all of the mole ratios you can get out of this equation. So, you can do a mole ratio between, whoops, those 2, these 2. This always reminds me of foil, actually. Oops. Oh. And this one and this one. So right there are 3 mole ratios. Turn them on their head, how many mole ratios do you have? If you do them all in reverse and count that as another one. You've now got 6. So then you can also do this to this, this to this. Now we have 1, 2, 3, 4, 5 turned on its head. That's 10. Plus, you can do those 2. 11, 12. 12 mole ratios out of that. Are there more that I'm missing? I don't think so. So I'm going to go ahead and let you get started on practice with these on homework, because you do have some practice just getting mole ratios. So chapter review Numbers 1 and 2 basically reinforce the concept we just did. And I'll put those up on the board. That's the start of the Chapter 9 homework. I should have at least the workouts done by the end of the day today, and I'll try to have the multiple choice done by Monday. So that's all I know. Questions, comments, concerns? Good. Have a good weekend.